So today we're going to introduce topics covered in your textbook, Chapter 9, on chemical reactions. This is going to be actually it's a superficial review of chemical reactions in general, but it's entirely appropriate for this course. So I'm going to share the PowerPoints for Chapter 9. And make a slideshow. All right, I need to do something else here. There we go. From the beginning. Here we are. So there's Chapter 9. Chemical reactions. So I normally skip over the outline, but I think an outline in this case would be helpful to put things in perspective. We're going to look at the types of chemical reactions, and those include both redox and non-redox chemical reactions, and that will probably give you pause because we haven't defined that term yet. So hold on, we'll get there. We're going to discuss one of the major theories for how to explain things that happen during a chemical reaction. We're going to describe chemical reactions in general terms of their heat production or absorption, which is often identified as thermochemistry. Then continue there with various factors that affect the chemical rates, what makes a reaction go fast or go slow, and then dovetail that into chemical equilibrium. And you'll see when I get there that the studying the chemical rates is important to be done first. Then we talk about chemical equilibrium, and of course we'll have to define it. What are equilibrium constants? How are they used? And then finally we'll close it out with how equilibriums change depending on what we do to them. Okay, so let's get started with chemical reactions. By definition, a chemical reaction is any process in which one or more substances we call reactants is transformed into other substances. And these products have a unique identity separate from the reactants. So if they have the same identity, then we have not experienced a chemical change. That falls under the heading of physical change, if the identity of the substance has not changed. And there are various ways to characterize the identity of substances, and we'll bring those out as we proceed through the chapter. One way to classify reactions is, in general, what happens during the reaction. And these are various types of chemical reactions described here, actually listed here, and we'll describe them one by one, whether it's a combination or a decomposition, displacements types of reactions, or, as I mentioned earlier, the redox types, the oxidation reduction reactions. And we'll get to those. And the important thing to remember is these are characterizations, they're categories for reactions. And many times, one reaction will fit into more than one category. So what's a combination reaction? In general terms, we have one reactant, one product that are simple, and very often they're elemental, and they form a compound. Examples. Here's calcium metal, and here's sulfur solid. When they combine, they can make a compound, calcium sulfate. The identity of calcium is distinct from sulfur. Right? Calcium is a metal, sulfur is a nonmetal. Calcium sulfide is a compound that has an identity, characteristics that are unique. They're nothing like calcium and they're nothing like sulfur. That's a combination reaction. Now, if we take a compound like calcium sulfate or some other, and we run the reaction in reverse, that's a decomposition. So we take a compound and we break it into smaller pieces. Very often those pieces are elements. And in its purest form, that's the description of a decomposition reaction. It takes a compound and makes it element. Here's an example. Copper 2 oxide. When we break it apart, copper 2 oxide has its own characteristics, physical and chemical characteristics. And when we break it apart, we get this metal plus this gas. So the difference between the reactant and the products is not just unique, it's stark in form and function. Displacement reaction. So let's say we take a compound and we combine it with an element. And the element replaces one of the members of the compound. And now that member of the compound is an element. That's a displacement reaction. In this case, X replaced Y. Example, iron metal reacts with copper sulfate and releases copper metal and iron 2 sulfate. That's a displacement. As I said before, these classifications can overlap. This reaction is also an oxidation reduction reaction, right? And I'll have to describe that to you in subsequent slides. But it's just a point to be made that this is not just one type of reaction. An exchange reaction, often called a double replacement reaction, is where you have two compounds and one element changes places with another element in the compounds. So in this case, you could look at it in terms of A replaces B or X replaces Y, but they swap places. An example, silver nitrate. In aqueous solution reacting with sodium chloride, swaps places. Sodium replaces silver in this compound. So now we have sodium nitrate and silver chloride. So there's your sodium nitrate, there's your silver chloride. And as it turns out, this particular reaction produces a solid. Silver chloride precipitates. That's the word we use for a solid that forms when two solutions react and produce a solid. We call it a precipitate. And this is typical of exchange reactions or double replacements. It's not the only way, of course. That's not the only way that they occur, but this is very typical for double replacement reactions, and they very often produce a precipitate. Think of it this way. If everything's in solution, what does silver nitrate look like? In aqueous solution, it's really not like that. It's really like this. Okay, it's really separate ions. So if you have these as ions, and then the other reactant as these ions, what kind of possible reaction could you get? Well, if everything is still in solution, you don't have a reaction, right? If these are all in solution, right, nothing happened, nothing changed. So in order for this reaction to proceed, we have to form a solid, or we have to form a gas. We have to form something that separates the product from the reactants in this form. And that's why these reactions very often form these precipitates. The formation of the precipitate drives the reaction to the right. Okay, let's look at another one. A combustion reaction. Right? Here we have a compound and an element. But the element doesn't just replace one of these elements. So it's not a single replacement. This combustion reaction is always involves oxygen. If somebody says they have a combustion reaction to describe, you know that one of the reactants will be oxygen every time. And then you'll have something else to react with it. It could be one reactant, it could be more than one reactant. In this case, we have propane, just like the stuff that you hook up to your grill and cook outside. Or some houses actually are heated by propane, and those tanks outside. Well, this propane can react with oxygen as it should and produces carbon dioxide and water. And combustion reactions are all exothermic. They produce heat. They are also all oxidation reduction reactions. Okay. And this reaction is balanced. You can confirm it for yourself. There are 10 oxygens there. We have 6 here and 4 there. We have 8 hydrogens. There's 8 hydrogens. 3 carbons, 3 carbons. So it's balanced. So what type of reaction would this be? Where you have a compound and it produces simpler compounds and elements. Well, obviously, that's a decomposition reaction. You're going from complex to less complex, or complex to simple. How about each one of these? What type of reaction do we have here? Well, there's an element, there's a compound. Now we have a compound and an element. Did this element originate in the compound? Yes, it did, right there. Did this part of the compound originate as an element? Yes, it did. So what kind is that? A single replacement reaction, or a displacement reaction. Authors vary on the way they classify these reactions. So this displacement reaction may also be referenced as a single replacement reaction. How about this one? There's a compound, but it makes a more complex compound. This would be classified as a combination reaction. Right? Often, this is also referred to as a synthesis. How about this one? Well, I jumped the gun. Notice there's oxygen here. And the oxygen reacts with this compound to produce other compounds. This is a combustion reaction, simply because it has oxygen. Okay, what do we mean by oxidation reduction? Okay, oxidation reduction in its simplest definition is during a reaction, electrons are transferred. That's it. That's the basic definition of a redox reaction. And we say redox rather than the oxred, right? Oxidation reduction, oxred, it just doesn't sound right. So we say redox. So anytime electrons are transferred, you have a redox reaction. Now, how do we determine that a redox reaction has occurred? You need some way of bookkeeping to determine whether electrons have been transferred. And we're going to get that in the subsequent slides. I was just checking myself. Now, if no electrons are transferred, that's a non-redox reaction. And there are lots of those. A clue to whether you have a redox reaction, and this is simple, rule of thumb. If you have a reactants where you have an element and a compound, such as methane and oxygen. Well, let's not do it that way. I'll tell you why I did that later. We have now carbon dioxide and water. Now let's balance this. Let's see, there are 3 oxygens there. So, and we need 4 hydrogens. So now we have 2, 2, and we need 2 there. So the equation is balanced now. Whenever you have an element on one side and it's in the compounds on the other side, you have a redox reaction every time, without fail. Now, in subsequent slides, I'll prove it to you. But this is a rule of thumb. Now, that element, it could also be on the product side. I mean, or it could be on the product side and not on the reactant side. As long as you have an element on one side that either is incorporated into a compound or is derived from a compound, you have a redox reaction. So that's what that red statement is down here. It's a quick way to answer a question. Is this a redox reaction? Well, if you do have that case, then it is. Now, if you don't have that case, it may still be a redox reaction. You have to go through the process of determining whether electrons are transferred. And we're getting to that right pretty quick. And we do it with a bookkeeping scheme called oxidation states or oxidation numbers. All right. So it's often mistaken that the oxidation number is equal to charge. Right? If you have a charge like sodium ions, right, that has a definite charge. It lost an electron. So it's a positive charge. Oxidation states can be charges, but they don't have to be. This, like I said, this is a bookkeeping scheme. So it's easy to mistake oxidation number for a charge when it's not. It's not always. All right, so we need to run through the rules. How do you determine oxidation state? And this is it actually references where are the electrons most likely to reside if they were to be transferred. Now, if you have a covalent bond between 2 elements, for instance, like water, the electrons are actually shared between the 2. But when we're trying to determine if electrons are moving, we use this bookkeeping scheme. And we say, okay, oxygens are going to be +1 oxidation state, and oxygen then will be, 2 minus. Now notice that the oxidation states, 2 pluses and a 2 minus, they balance. So that's part of our bookkeeping. But oxygen doesn't actually have a 2 minus charge. It's in a covalent system with hydrogen. The electrons are shared. But oxygen gets the negative number because it's more electronegative than hydrogen. In other words, it has a stronger pull on electrons. Even though it can't develop the full charge, for our purposes of our bookkeeping, we say it has an oxidation state of 2 minus. Okay, so let's see. We've got some rules coming up here. Okay, if you follow these rules for determining oxidation states and how they interact with one another, then you should be able to work problems that involve redox reactions. Oxidation state for an element is always taken as 0. So if we were talking about sodium metal, its oxidation state would be 0. And notice where I put that 0. Remember early on in this course, when we have the symbol for the element, there are 4 places around here. I said they were reserved for basic information, like the atomic number, or the mass number, or the number of atoms, or the charge. Well, now I'm expanding that. Where this used to be only for charge, now we can have oxidation number. So if you have an oxidation number for an element, you put it in that spot. And in this case, for elements, in their standard states, are always 0. If we have an element that is charged, like sodium ions, Na+, that charge is the oxidation number. So we keep it simple. Right? If it's already got a charge, why complicate things? Right? That is its oxidation number. We also have identified oxidation numbers for some elements in the periodic table, and they're always going to be that number. We assume that they're going to be that number. Group 1A, alkali metals, the first column on your left in the periodic table, they are always taken as +1. So that would be lithium, sodium, potassium, rubidium, cesium. All of those are +1 when you find them in a compound. The same thing for the next group, the second group, alkaline earths. They're always taken as +2. So that would be beryllium, magnesium, calcium, strontium, barium. They're always +2 in compounds. Okay? The oxidation number for hydrogen is +1 in all covalent compounds. So if hydrogen is in a covalent compound like water, it's always taken as +1. Or I'm trying to think of other types. Hydrogen chloride or hydrochloric acid, whichever the case may be, it's always +1. Okay? There are circumstances where hydrogen takes on a different charge when it's in combination with a metal. For instance, I'm trying to think of a good one. How about this one? Lithium and hydrogen. In this case, lithium is +1. It can't be anything else but +1. So that means hydrogen has to be -1. Okay? In that case, hydrogen is not +1. It's -1 because it's in combination with a metal. This is lithium hydride. So if the hydrogen is combined with any nonmetal in a covalent compound, it's going to be +1. In most cases, oxygen is taken as -2. So water would be -2. Okay? Except for peroxides. So what's a peroxide? A peroxide is 2 oxygens bound together, and these are covalent compounds. Oxygen bound together, and then on either end is something else. Right? Some element or groups on either end. That's why we use R, because there's no element in the periodic table that goes by R. So we can use R as a placeholder. If this is hydrogen and that's hydrogen, you have hydrogen peroxide. Same stuff that's on in your medicine cabinet or under your sink in the kitchen. Hydrogen peroxide. In those cases, both of them together, -2. So each oxygen is only -1. That's a special case for oxygen. Any other time, oxygen is taken as -2. In binary molecular compounds, that means in binary covalent compounds, the more electronegative element is usually assigned the negative oxidation number. And it's equal to its charge if it were combined in an ionic compound. Right? So that's the case for oxygen in an ionic compound like sodium oxide. This would be +1 for each one, which means a total of +2, which means the oxygen has to be -2, right? That's one of the rules we haven't got to yet. That's rule number 7 here. These values always have to add up to 0 for a neutral compound. So that would be -2 for the oxygen. Oxygen is more electronegative than sodium. So it stands to reason oxygen gets the negative, sodium gets the positive. And then 7, all the oxidation numbers in a compound must add to 0. But we do have covalent polyatomic ions. Such as the carbonate ion. Right? So the carbonate ion, we work from the more electronegative one, oxygen. That's a fixed oxidation number. So if this one is -2, then we have a total of -6s, correct? 3 times 2 is 6. So that means the addition of carbon must equal to -2. So what can you put there to make this -2 as on the other side? Carbon must be +4 to make a -2 total. Okay, so this is +4. Now here's the way I like to do it. Rather than write out a math equation, I just say, all right, this is -2 for oxygen. And by the way, that 2- is for the entire polyatomic ion. So 2- for each oxygen, -6 total. Then I'm going to hold 2 minuses in reserve. Right? Those 2 minuses are up here. So now all I have to do is balance that. There's my +4. It's a little, it just works better in my brain to do it that way. Let's try another one, another polyatomic. How about sulfite? But 2 minus for that one. Well, this one is -2, so it's -6 total, correct? We need to hold 2 of these minuses out. So this is also +4 for sulfur. Okay? All right. So let's see if we can determine the oxidation numbers for each of the elements in these compounds. All right? So let's take, what is that? Potassium dichromate. All right, it's a neutral compound. So oxygen is, well, let's start over here. Potassium is an alkali metal, so it's always going to be +1. Oxygen is -2. Right? So that's -14, right? 7 times 2, and 2 times +1, right? So what is that? Let's see, 14, oh, excuse me, 2. 2 times +1 is +2. So the difference is -12. So in order to make this compound neutral, the chromiums have to contribute +12. And since there are 2 of them, each one contributes +6. Okay, now we have the oxidation numbers for each one of the elements in that compound. All right, we just did carbonate ion, right? So we don't need to do that one again. How about the next one? Manganese 4 dioxide. Remember when we were naming compounds? This is a type 2 compound, and you have to know what the charge is. Well, by doing that, you know what the oxidation number is, right? MnO2. I said manganese 4 oxide. Oxygen is 2 minus. Manganese is 4 plus. And it just stands to reason. -2 times 2 is -4. So you have to balance it with a +4 for that single manganese. How about PCl5? Now what do we do? Well, in this case, we have to expand the rule. In fact, there was one rule that was not given in that group. I don't remember it. Fluorine is always, in a compound, fluorine is -1. In a compound, chlorine can be different oxidation states. But when it's in combination with a less electronegative element, you should take this one as a halogen, single charge only. So this one would be a -1 also. It's in the same group as fluorine. That way you can have a -5 here, and that means this is a +5. All right. So that's what we did there. We'll go ahead with SF4. Right. This is -1, -4 total. So this has to be +4. Okay. All right. Let's see, 9,4. Oxidation numbers. I'm going to have to move along here. Just understand that fluorine is the only one that's -1 fixed. It has no other possibility. Chlorine, bromine, iodine, they can have multiple charges, and all you have to do is look at your periodic table, and you can see in each one of those boxes, chlorine has multiple charges listed. Those are actually oxidation states. And bromine has multiples, iodine has multiples. I really would like to, I don't have time. I was going to go through the sequence of polyatomic ions with chlorine and oxygen, right? The chlorate is where I start, and then chlorite, and then hypochlorite, and then perchlorate. The chlorines in that sequence are different oxidation states for each one. Okay. In that case, you fix oxygen as -2, and then you calculate the chlorines. Okay, here's a metal and chlorine gas, right? You have a transfer of electrons, right? Calcium is an element, chlorine's an element, they're zeros. Calcium is an alkaline earth, it's +2. Chlorine is a halogen, it's -1. Right? So you see that electrons must have been transferred. Where did they go? Well, if calcium is now positive, it had to lose electrons. Remember, you can't get a positive charge by changing the protons. If you do that, you change the element. So the electrons had to move. So the imbalance in calcium now is toward the positive side because it lost electrons. Well, where did those electrons go? They went to chlorine. Chlorine now has acquired 1 electron each. And since there are 2 of them, there's a balance. 2 electrons were transferred from calcium to these 2 chlorines, giving you these oxidation numbers. So, what would be the oxidation number for sulfur in this compound? Right? Well, we know that hydrogens are supposed to be +1, so that's +2 total. Oxygens are -2, so that's -8 total. Right? So that's a -6 that has to be balanced by a +6 here. So sulfur would be +6. Okay, you need to be able to do that to determine the oxidation numbers for any element in any reaction. Otherwise, you cannot determine how many electrons and what direction they moved. Okay, we didn't define our terms earlier, we're going to do it now. Redox reactions always transfer electrons. But the oxidation has a definition, the reduction has a definition. Oxidation is the process where the reactant loses electrons. And reduction is the process where the reactant gains electrons. Right? How do you get that straight in your mind? Let's see if I put it in here. Yes, it's on this slide. Use the mnemonic. Oil rig. Oxidation is loss. Reduction is gain. Very simple. One of the better mnemonic devices. So oxidation, you have to lose electrons. So notice, I'm going to use an example here. Let's do that one. Okay, so we need 2 irons and 2 aluminums. And we have 3 oxygens and 3 oxygens. Okay. This is an extremely exothermic reaction. It's called thermite. This mixture here and here is thermite. It is an oxidation reduction reaction. How do I know? Well, my rule of thumb says there's an element, but it's in a compound over here. and it's in a compound here, it's an element over here. So I know it's oxidation reduction. But which one's which, right? Okay, so this is an oxidation state of 0, and that's a 0 because they're elements. This is a -2, that's a -2. So that's -6. That means this has to be +6, and each one is +3. Okay? Same thing over here, same logic, +3. Okay, now which way did the electrons move? Well, this is a +3, and it's going to 0. So how do you get there? You have to add 3 electrons. So we've gained 3 electrons per iron times 2 equals 6 electrons total moved. So this one had to go from 0 to +3, right? So how did it get there? Well, it lost 3 electrons. Per aluminum times 2 aluminums equals 6 electrons. So the same amount gained and lost. That's balanced electron movement. It's required for a balanced equation. Okay, so which one's being oxidized and which one's being reduced? Right? Oil rig. Oxidation is loss. This is oxidized. This is reduced. Okay? Now notice that oxidation and reduction never occur by themselves. They're always in pairs. If you have an oxidation, you automatically have a reduction because the electrons are moving from one place to another. So that means that this reduction makes it the oxidizing agent. It's responsible for the oxidation of that element. And this one is the reducing agent. It's responsible for the reduction of that iron. That's what these statements mean. The one that is oxidized is always the reducing agent. The one that is reduced is always the oxidizing agent. Okay, this puts everything together. I've already said that they always occur together and so forth. So that came straight out of your book too. If you need more discussion of that topic, then go to that table, and in that vicinity, you will have more discussion from the authors of the textbook. So what's happening to the numbers? With oxidation, the number increases. It may go from a more negative to a less negative, right? From -7 to -5 or -4, but it's still increasing. Reduction, on the other hand, decreases. It goes more negative, and that stands to reason. If you add electrons to be reduced, then you're adding negative charges. So the oxidation number should become more negative. So what's happening here? What's oxidized and what acts as the reducing agent? Right? So whatever is oxidized also acts as the reducing agent. So what's oxidation is loss. So who's losing electrons? Well, copper is 0 there, and over here it's 2+. So it lost electrons. So copper is oxidized, and copper is the reducing agent. All right? All right. Let's take these examples. And in order to proceed, what do we need to do? Well, at this point, we're assuming that these are balanced equations, and in fact, they are. All we need to determine to answer the question is which of these reactions is a redox reaction, and then identify the oxidizing agent and the reducing agent. Okay? So the first one, well, I thought they were going to give us more information, so we're going to have to do it ourselves. We know that this one is an oxidation reduction reaction. Why? Because there's an element here and it's in a compound over here. Or it's in a compound here and it's an element there. So we know it is. But we need to determine which one's the oxidizing agent and which one's the reducing agent. So this one is 0, oxidation number. A good bet is that the hydrogen is involved here in change. So in this one, it's +1, that's -1, yields (2,2H2). And this one's 0. Right? So we went from 0 to +2. So we lost 2 electrons. So if this one is oxidized, it must be the reducing agent. Correct? And if this one is reduced from +1 to 0, it must be the oxidizing agent. So we know that that is one of the, okay, zinc is the reducing agent, yes, because it was oxidized. And HCl is the oxidizing agent because the hydrogen was reduced. Okay, how about this one? B. Let's see, dichromate ion plus hydroxyls yield, and I'm going to put it over here, 2 chromates plus water. Okay. So what's what here? If this is a +1 and this is a -2, then that gives you the charge. This is 2 times 7 is -14, but we need to hold out. Wait a minute, this is -2 here. 14, we need to hold out 2, so that's 12. So this has to be +12, which means +6. How about over here? Well, -2 times that is -8. Hold out 2, -6, +6. No change on the chromium. How about the oxygen? Oxygen didn't change. Hydrogens didn't change. This is not a redox reaction. No electrons were transferred in this reaction. Notice also that that's a anion and that's an anion, right? So we have to assume that this is a net ionic equation. There are cations attached to this, like maybe sodium or potassium, and maybe sodium and potassium here, but they're spectators, so they don't count. We leave them out. All right, that's not redox. How about C? Well, notice you've got copper here in a compound, and over here it's an element, so that's definitely redox. We just need to say how it operates. Okay? All right, so here, this is a -1, so that makes this a +1. There's 1 to 1. Here's -1. This has to be +2. And this has to be 0. Right? So, where's the oxidation? Well, notice there are 2 of them here. right? One of those takes this +1 and goes here. So that one is oxidized. Makes it the reducing agent. This one goes here. It's reduced, which makes it the oxidizing agent. Okay. This is a special type of reaction called disproportionation. I know it's a long word, but it just means that this compound went two different directions. Some of it went here, some of it went there. Actually, some of it went here and there, and then the other one just went here. So copper 1 chloride is both the reducing and the oxidizing agent in this case. But this one can't be the same at the same time. So one of those does one function and the other does the other function. All right. So let's see, it's 10 o'clock. I got 1 hour left. All right. So what do we mean by collision theory of chemical reactions? Well, from the name, we know it's a theory, so it tries to explain why reactions occur. And then the other word, collision, means somebody's got to smack into somebody else. We've got to have an impact somewhere. So it does, the collision theory does say that collisions are involved and they have to impact one another with sufficient energy to make the reaction occur. That's the activation energy. But it's also important that the reactants collide in the proper orientation. If we're going to have new bonds formed on this side of the molecule and on that side of the other molecule, then if they hit this way, nothing happens, no matter how much energy. But if they happen this way, then you can get old bonds broken and new bonds formed. So that's the requirement of collision. They must come together. Otherwise, a reaction will not occur. And they have to have enough kinetic energy. So what does that mean? Usually that means temperature. The higher the temperature, the more kinetic energy each molecule has. Temperature is a measure of the average kinetic energy of all the molecules and atoms in the mixture. Right? So they all don't have exactly the same kinetic energy, but the temperature gives you an average measure of that kinetic energy. And as you increase the kinetic energy, you increase that average kinetic energy. So that means all of the molecules that collide may not have the proper kinetic energy, right? When we look at it this way, right? This is numbers. Let's see, no, excuse me. Numbers of atoms, molecules, and this is the kinetic energy. Then as the kinetic energy increases, you get the famous bell curve. So most of them are right here, but you have some out here and some out there. So anything above a certain level, if this is the activation energy, then all of these have sufficient energy to react, and these do not. So if you increase the temperature, then what you do is you shift this whole curve up, and that puts more of the curve past the activation energy. Then you can get reaction with more molecules when they collide. And then, of course, the orientation depends on, well, that is one determining factor of the reaction. They have to be oriented correctly when they collide. So here's your author's pretty picture for what may happen. If this nitrogen dioxide comes into contact with carbon monoxide and they're properly oriented, right, you're going to form a new bond here with this oxygen, and that will give you carbon dioxide over here, and that leaves this nitrogen and oxygen together over here, right? That's proper orientation. These others are not oriented correctly. Okay, so just to review, 3 factors necessary for a chemical reaction. Well, you need, you have to have a collision, right? You have to have the proper activation energy, and you have to have the proper orientation. So that's required. So what happens during a reaction? Let's see. I'm checking myself for the next slides coming up. Yes, we do have that discussion. Okay. In its simplest terms, an exothermic reaction is one that releases energy during the reaction, right? Where is that energy, right? If you have reactants here, and they yield products over here, and it's releasing energy, right? And we designate that with a delta H. Just think of it as heat, right? Releasing heat. Where'd that heat come from? It came from the bonds. The bonds that were broken here and reformed over here, these bonds have more energy than these bonds. If these bonds have more energy than those, then when you get some of that energy back by reforming these bonds, you don't get all of it back. And that's released as heat or some form of energy. This is an exothermic reaction. The endothermic reaction is just the opposite, right? This would be like this. That has lower energy and higher energy. So that means it has to absorb heat because these bonds are less energetic than these bonds. And that energy has to come from somewhere. So it sucks it away from the environment. That's why these reactions feel cold when they happen. Whereas the exothermic reactions feel hot. This is what it looks like in diagram. So as the reaction proceeds, excuse me, accidentally touched that. As the reaction proceeds from left to right, you have reactants on this side, products over here. This tells you the total energy that's contained in the reactants. And this is the total energy contained in the products. Right? So the difference between their energies at this level and that level is the amount of energy that's released. If this side's lower than that side, the energy has to be released. And that's this energy liberated. That's an exothermic reaction. Now, this reaction won't proceed on a molecule by molecule basis unless the reactants collide with this much extra energy, right? That's the kinetic energy, not the energy in the bonds. This is the energy in the bonds. This is the kinetic energy of the collision. So if it has that much energy in the collision, it will make it over to the other side, and now you get products. Okay, so that hump right there, between here and the top of that hump, that's the activation energy. This difference is the liberated heat, or the delta H. We call it enthalpy. Okay, endothermic reactions, like I explained, here's a very good example. Photosynthesis. That's what plants do. They take energy from the sun and they store it in the bonds of the molecules that they're building. They take carbon dioxide and water and make carbohydrates, right? Starches, sugars. They make those, and that stores energy, either for later use by the plant or for building itself, right? Cellulose, which is a major component of tree trunks, is created by this process and subsequent reactions, of course. But originally, they're taking energy from the sun and storing it in molecules. And this is what that energy diagram looks like. So the energy of the reactants is low, and the activation energy there is very high, right? Because you're going from here all the way up to there. And then if you make it to that height, you go over the edge, and now you're at this level. So you have more energy in the products than you did in the reactants. That is an endothermic reaction. Notice that if you run it backwards, right, just flip it around, and you add just this little bit of energy, then you can get the products to go back to reactants. Which of these are correct? Well, I'm just going to go to the answer because I'm running out of time. During an exothermic reaction, the average energy of the products is lower than the average energy of the reactants. If the products have less energy, that energy had to go someplace, and it shows up as heat, an exothermic reaction. Now let's talk about reaction rates. What do we mean by reaction rates? In its simplest term, how fast do the reactants convert to products? We may express that in terms of, just in terms of the reactants. You know, how fast did the reactants disappear? If we know the balanced equation, then we know that if they disappeared over here, they're going to show up there anyway. So really, to express the reaction rate, all we need to know is how fast did the products disappear? I mean, how fast did the reactants disappear to produce products? What affects the rate of a reaction? Well, the physical nature of the reactants. What do we mean by that? Well, could be solid, liquid, or gas, right? If they're gases, they have intimate mixing of all the reactants. If they're liquids, then you got to be sure they're mixed, and the form that they're in makes a difference. Solids, the best way to increase the rate of reaction for a solid is to break it into smaller pieces. Grind it into a powder. More surface area means more contact, right? More collision possibilities for your reactants. The reaction rate is also dependent upon concentration, right? If you say you're in an aqueous solution, the reaction rate is going to go faster if the concentration of the reactants is higher. Why? Based on the collision theory, there's more opportunity for collision if the concentration is higher. It just stands to reason. And if there's an activation energy required, which there always is, for that reaction, then you can speed it up by increasing the temperature. You increase the kinetic energy of the molecules, they collide with more energy, the reaction is more likely to occur. And the last one, catalysts. So what's a catalyst? A catalyst is a substance that's added to a reaction mixture that is involved in the reaction, but it's unchanged in the products. So you put something in on one side, comes out on the other. A perfect example of that is hydrogen peroxide plus potassium iodide. You've still got potassium iodide on this side. That's the catalyst. But now you have oxygen and water on this side. So this decomposed, and if you don't have the catalyst, that reaction will still happen, go from here to here. But with the catalyst, it goes faster. So the iodide is the part of that molecule that's the catalyst. Potassium is a spectator. So here's a detailed description of the physical nature of the reactants. Like I said before, the physical state makes a difference, and the particle size makes a difference. Particle size, we usually reference solids. When all the reactants are in the same physical state, we generally see a faster reaction. Let's see. Well, okay. Back up. When the reactants are in the same physical state, what if they're both liquid or both solid or all solid or all liquid reactants? The liquid phase tends to react faster than the solid, simply because of the collision theory. They're more likely to collide if they're both liquids than if they're both solids. And the fastest rates are observed among gaseous state reactants for the same reason. You're more likely to get collisions that result in reactants if the reactants are gaseous state. So the best way to get a solid to react faster is just to break it into smaller pieces. Just grind it into a powder. Notice that in a coal-fired power plant, what do? Or what's done for them when the coal arrives? It's ground into a powder. Actually, when it arrives, it might be chunky. But before it goes into the burner, into the furnace, that coal is pulverized into a fine dust. That's so that there's more surface area, more collision possibilities with the oxygen in the atmosphere that is driven into there along with the coal. Right? The reaction is faster, and faster reaction rates mean more energy produced per unit time. Now, if the particle size is small enough, you can get explosions. And that's just an accelerated speed of reaction for an already existing reaction. Like coal dust reacts with oxygen. If the coal dust is fine enough and a high enough concentration, then you can get a mine explosion. So that's why it's so important to keep mine shafts well ventilated, to keep the coal dust blown out of there. All right. And here's a reference to concentrations. If you increase the concentrations, you increase the reaction rates. That simply means that there are more molecules available in the reaction mixture to collide with one another. It's a very simple concept. Increase the temperature, you increase the activation energy. And the collisions are more likely to result in reaction. Now, there's nothing we can do about orientation. That's random, right? All we can do is change the temperature and just hope that we get more collisions that are oriented correctly to produce a reaction. And the presence of catalysts. How a catalyst works, without the iodide in this case, right? This decomposes to that by a certain pathway. It goes through steps to produce these products. When you provide a catalyst, the catalyst offers an alternate pathway to go from here to here. And those alternate pathways individually are faster than the non-catalyzed pathway. That's how you get the increased rate. Now, it also, what it does is it lowers the activation energy. So if we draw the picture, the graph, so here's your energy and here's your progress, right? And your reaction goes like this, like that. Your activation energy is here, right? That difference. But for a catalyzed reaction, that same reaction goes like this. Now the activation energy here is the catalyzed activation energy. So what does that mean? That also means, in addition to the pathway, it means that more collisions meet this criteria of a lower activation energy. So you get more reactions in unit time. There's a special type of catalyst that biological systems use. It's called an enzyme. Enzymes may be classified in general as catalysts, right? Biological catalysts. But enzymes actually are a step above inorganic catalysts. That is, catalysts that we would use in just a purely chemical reaction. Enzymes have some characteristics that are superior to inorganic catalysts. In the first place, they're much, much more efficient. In the second place, they offer more control of the reaction. In other words, sometimes an enzyme must be activated before it works. It can just sit there and wait until you need it. And then under the right conditions, it's activated and then it works. And usually, not always, but usually enzymes catalyze reactions in one direction only, or they prefer one direction catalysts, which means you control reaction going forward only. And if you want it to go backwards, you need a different catalyst. Now, that's not always the case. You do get reverse reactions with the same enzyme. But many biochemical reactions are controlled in that fashion with two different enzymes. One of the downsides of enzymes is they have a very narrow range of conditions in which they will operate correctly. Usually that means temperature, a very narrow temperature range, and ionic conditions and acid conditions. Now, we're not going to get to acids until next chapter, but those are conditions that restrict the application of the enzyme. That's why it's so easy for a system, a human system, for instance, to go haywire, right? When your temperature goes way high, then your enzymes don't work right. They stop functioning correctly. Or if you're diabetic and you go into ketoacidosis, then that increase in acid in your system interferes with proper enzyme function. Okay, so, oh, I didn't realize I should have looked ahead. There's the diagram I drew earlier. This is the change in activation energy for a catalyzed reaction. That's typical. Every time you use a catalyst, if the catalyst does indeed increase the rate of reaction, this is one of the reasons that it does. All right, that's simple definition of a catalyst. Increases the rate of reaction by decreasing the activation energy. That's a very simple definition and accurate. Now, how about equilibrium? We talked about reaction rates first because equilibrium says that both forward and reverse reactions are possible. When you have these reactants producing those products, well, sometimes those products can react and reverse the reaction. Okay? Now, it varies depending on the specific reaction. Maybe the tendency is to be all the way over here, or mostly over there, or mostly over here. And we need a quantitative description of how that occurs. Well, first, we have to know, well, we're going to introduce the concept of reaction rates into this model, because we just learned that the reaction rate will go that way, right, at a certain rate. And there's a K value involved. You don't have to know where this K came from, but that K describes the forward reaction. And then there's another K for the reverse reaction. So when the forward reaction rate and the reverse reaction rate are balanced, they're equal, then you have equilibrium. And on the surface, from looking from the outside in, the macroscopic view, it looks like there's nothing happening, right? You have a certain amount of A and B, and you have a certain amount of C and D, and they don't change. The concentrations do not change. But we know on the microscopic level that there's always forward and reverse reaction happening. It's a furious activity, going this way and that way. But what we observe from the outside is that it's static. So when you first start off with this reaction, say we're taking hydrogen and iodine to produce hydrogen iodide. In the beginning, at the very beginning, you have all reactants and no products. But as the reaction proceeds, you have less and less reactants and more product. And at some point, they balance based on the reaction rate. Okay? So the rate of disappearance of the reactants now equals the rate of appearance of the product. Now you have equilibrium. This is just another way to look at it. And we usually discuss, in fact, we always discuss equilibrium in terms of concentration. So, and typically the expression is in molarity. That is the best way to do it, unless all of your reactants and all of your products are gases. If they're all gases, then you can describe this in terms of not just molar concentration, but in partial pressure, because partial pressure is proportional to molar concentration. And sometimes it's easier to measure it that way. These reactions that produce significant return rates are known as reversible reactions. Theoretically, all reactions are reversible. They can go in either direction on the microscopic level. But as a practical yeah, painting myself into a corner. If the reaction is fast in one direction and slow in the other, in the reverse, then that reaction is considered irreversible at some point. So this is sort of a semi-quantitative or a qualitative expression, right? In reality, reaction is either reversible or irreversible. And it all has to do with the balance. If you get mostly products and very little reactants left over, we consider it irreversible in the forward direction. Notice that if you turn the reaction around, then a reversible becomes irreversible if you change products and reactants. So chemical equilibrium is reached when the concentrations of all the reactants and all the products remain constant. That's on the macroscopic level. The reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously and in sufficient quantities to maintain measurable amounts of both. So what would happen, this is sort of an intuitive expression, what would happen to this reaction? Let's say we have water in the gaseous phase reacting with carbon monoxide to produce hydrogen and carbon dioxide. These are all gases. Okay, we're at equilibrium. In fact, that arrow should be double barbed. We've reached an equilibrium state. And since they're all gases, what else do we know? The vessel has to be closed, enclosed, right? Otherwise, the gases will escape. So it has to be a closed vessel. And we've reached equilibrium. So what would happen if you add more water to the flask? You just shoot a little jet of water in there. What would you expect? Well, if everything is at equilibrium and happy right now, then these concentrations are fixed, right? They don't change. If we change them artificially, we put more water in there, what's going to happen? You can expect the reaction to shift to the right and produce more hydrogen, more carbon dioxide, and consume some of the carbon monoxide until a new equilibrium is established. Okay? Why? Well, you've increased the concentration of water, so there are more collisions of unreacted water with carbon monoxide. And you have a reaction that speeds to the right until the return reaction balances that speed. How about adding more hydrogen? By the same logic, it would go the other direction. It would go back toward reactants. Now, when you add that extra hydrogen, does the overall equilibrium hydrogen concentration increase? Yeah. You're not going to consume all of it. You're going to consume enough so that equilibrium is reestablished. So you increase the hydrogen at equilibrium and you decrease the carbon dioxide. And you increase carbon monoxide and you increase water. Okay. So how do we express that in quantitative terms? Well, we use what's called the law of mass action. So if here's the reactant and its balancing coefficient, and this one has a balancing coefficient, and this one has one, and this one has one, that should be a small y. Actually, I like it better this way. If you have an A here, and a B here, and a C there, and a D there, then you can tell which one belongs where. So the equilibrium constant, that K is a constant for any given temperature, is equal to the product concentrations, each raised to its power of the coefficient, divided by the reactant concentrations, each raised to their power. Now we use square brackets to indicate that the concentration of this component is measured at equilibrium. Once equilibrium is established, then we have that concentration. It's not the concentration at the beginning. It's when equilibrium is established. And then we raise them each to the power of their balanced equation, right? So here's another case where you can't proceed unless you balance that equation. If it's unbalanced, you can't write that expression. Okay. We always put the products in the numerator, and we always put the reactants in the denominator. And this one times that one, each raised to its respective coefficient power. One other thing is that when we write these expressions, there are some terms that we just leave out. Pure liquids and pure solids. So if you have a solid or a liquid in your balanced equation, they do not go in here. Only aqueous solutions and gases go in there. Now, why is that? Well, primarily because if they're pure liquids, their concentration doesn't change. And pure solids, their concentration doesn't change either. That means they're still part of the reaction, but they don't have any influence on the equilibrium. So we don't put them in there. Or you could view them as if their values are buried in this value. They're not over here, they're over here. Either way, we don't use them. Okay, so we're getting into Le Chatelier's principle now. Oh, by the way, while I'm here, what does this say about the K value? If you're mostly products at equilibrium, the K would be very large, extremely high, greater than 1. And then these would be very small. It's just the nature, the math nature of the quotient. If this is big and that's small, then this is going to be large. On the other side, if this is small, you don't have much product, and this is large, then the K is going to be very small, a smaller, less than 1. The other thing that we don't do is we don't put units of measure next to the K. It's just too confusing, because in any balanced equation, you can have any combination of coefficients, and those powers in your expression will give you some really strange units of measure. So we just take extra care in balancing the equation, writing the expression, and then when we evaluate it, the answer we can expect to be correct with its units. And any reference source for these values, just lists and lists of them for each equation, they will not have units of measure with them. They will say, though, these equilibrium constants were determined using molarity or using partial pressure for gases. In those cases, then they will designate, because the K will be different if you use molarity or partial pressure. Okay, so in this case, we discussed earlier what happens when you change concentrations, right? That's Le Chatelier's principle. Which, let me see, is it going to be given to us here? Yeah, we're going to get to it in a minute. So I'm not going to define it right now. We're going to talk about it in practical terms. If you change the concentration of a system at equilibrium, and if you change the concentration of reactant or product by either addition or subtraction, doesn't matter, then the system will move to mitigate that disturbance. In other words, if you remove something from the product side, it'll make more product until equilibrium is reestablished. Or if you add something to one side, it'll consume part of that until equilibrium is reestablished. That discussion is for concentrations. The other possibility is, what if you change the temperature? Well, what actually happens is when you change the temperature, the K value changes. And then you can calculate a different K. And if the K changes, that means the equilibrium distribution shifts. But there's a practical way to approach this also. If you have reactants yield products, if it's exothermic, you can treat the heat as a product. So this is exothermic, releases heat, okay? So now, if we change the temperature, what are you doing? If you increase the temperature, you're adding this component, and it makes the reaction go back that way. But if it's like this, and you cool it, you decrease the temperature, then you're removing that as a product, and it shifts the reaction to the right. Okay? The other possibility is endothermic, where heat goes into the reaction as a reactant. In that case, it's just the opposite. If you increase the temperature, you will increase the rate of reaction. You'll shift the equilibrium toward the product. I should do it like this. But if you decrease the temperature, then you're shifting this direction. You're removing heat. And now you're favoring reactants. Okay? I mentioned this earlier. If KEQ is very large, then the system tends to be more product than reactants. If the KEQ is small, less than 1, the equilibrium system tends to be more reactants than products. Now, there's a difference between I'm going to leave that there for now because there's one other term that we haven't discussed. The equilibrium position is not the same as the equilibrium constant. The equilibrium constant is constant for a fixed temperature. But the equilibrium position is an indication of actual concentrations of reactants and products. So if you add a reactant, then the position of the equilibrium shifts toward products. But the constant doesn't change. Once you reach equilibrium, the constant is a constant. So there is a difference there between position and constant. This is a comparison of K values, right? If they're that large, that reaction essentially goes to completion. Or if they're this small, 10 to the minus 30, you essentially have no reaction in the forward direction, right? And that's another thing. When you say the reaction goes to the right or to the left or forward or backwards, those terms have no meaning unless they reference a balanced equation. If you got the equation to talk about, yeah, okay, I'm talking about this equation. We're moving to the right. Okay, I know what you mean. But if you say, we have this reaction I'm talking about, and I don't describe it, I say, the reaction moves to the right. I say, what do you mean? Is it this one or this one? Or is it some other one? You have to reference a balanced equation if you're going to use terminologies like shift to the right, shift to the left, favor products, favor reactants, things like that. A balanced equation is absolutely essential. So what would be the equilibrium expression concentration for this reaction? Hydrogen and iodine yields hydrogen iodide. Okay, we have to assume that there are no solids or pure liquids here. So we're going to use every term, okay? So this one would go on top. These two would go on bottom, correct? So it's either this one or this one. You never use a coefficient in an equilibrium expression. It's always the power. So that 2 goes up here. D is the answer. That's the correct expression. Now, Le Chatelier's principle. Okay, I'm just about done. Le Chatelier's principle simply states, like I've said before, that if for a system at equilibrium, when a stress is applied, whatever the stress may be, the system will react. It will readjust in a direction that reduces the stress. Right? And we talked about concentrations. We talked about temperatures. The other one we haven't discussed is pressure. If you change the pressure on a system, what effect does it have? If the reactants are in solution, right, or in solution, solids, pure liquids, changing in pressure has no effect. Change in pressure only has an effect on a system, an equilibrium system, if there are gases involved. So how would that be? Well, let's say, trying to think of a good example. All right, let's take hydrogen and oxygen yields water. And in this particular case, water is going to be a gas. All of these are gases. Okay, so let's balance the equation. 2 hydrogens, okay. 2 oxygens we need here. So we need 2. All right. So at equilibrium, you have 2 moles of water gas on this side as product, and you have 3 moles of hydrogen oxygen combined on this side. If you put that, if that is in a cylinder with a movable piston, right, that reaction is in here, then what happens if you increase the pressure? And to increase the pressure now, you have to decrease the volume, right? Boyle's law. You push that cylinder down, that piston down, you increase the pressure. So what would reduce the pressure? That's the disturbance. You've increased the pressure. The system's going to respond to decrease the pressure. So how could it decrease the pressure? Reduce the moles of gases in that environment. So which way would it have to shift to reduce the moles? 3, 2. It would go to the right, produce fewer moles. that would be a response. Now, if we had equal moles on both sides, there'd be no response. It doesn't matter what you do, it's not going to change. Okay. So this is a statement of what I just gave you. You've got to have a balanced equation, otherwise right and left don't mean anything. Concentration change, we did that one. Right? It would shift to the side to consume some of the added amount, or it would shift to the side to replace some that was removed. Okay. This is your artist's idea of the Haber Bosch process here. So notice, these are all gases. I probably should have used that one as an example. 1 nitrogen and 3 hydrogens means what? 4 moles of gas total here. And 2 moles here. So what would happen if we increase the pressure here? Shift to the right, correct? Make fewer moles. If we decrease the pressure, it would shift to the left to make more moles. Okay. So this also illustrates what happens if you add hydrogen. Right? Notice that we still have some hydrogen left over here. That's more. 8.3 is more than 7. But the system has consumed some of the hydrogen. And in order to do that, it had to use up some of the nitrogen. So the nitrogen now is lower, the hydrogen's a little bit higher, and the ammonia is definitely higher. That's a different equilibrium position. But the expression for the equilibrium concentration, the constant, did not change. You could use these values and calculate the equilibrium constant, either with this one or with that one. You get exactly the same number, K. Okay, we talked about this one also, the effect of temperature. Sometimes you can see the effect. You know, if one or more of your reactants and products are colored, then you can see a change in color, and that's what we've shown here. Pressure. Okay, I discussed the change in pressure by volume change favors, if you increase the pressure, you favor fewer moles. But what if you put an inert gas in that reaction? That increases the pressure, doesn't it? Right? But it has no effect on the equilibrium because the inert gas isn't involved. You didn't actually change the number of moles of reactant or product. Right? So injecting an inert gas has no effect on the reaction. So just because you change the pressure, you need to know how the pressure was changed. And then there's the catalyst. The catalyst never changes the equilibrium. Right? The catalyst changes the speed of the reaction, both forward and reverse, actually. So when it does that, it changes the rate of a reaction, but it does not change the equilibrium. Okay. So these are possible factors that could be taken into account in Le Chatelier's principle. Concentration, temperature, pressure. Let's see, I got 10 more minutes. I'm not sure if we got time to do this one. A breathalyzer, right? What does a breathalyzer do? Well, it's for field testing, sometimes, the amount of alcohol in your system. And it's calibrated so that the arresting officer can check you for legal limits. And this is one of the possibilities, the reactions that it will do. This type of reaction may require, excuse me, a larger machine at the police station. But this reaction is used. In this reaction, what is undergoing reduction? So that's it. We're done for chapter 9. Next Friday, we'll do chapter 10, and then we'll follow up the next week with review. And the last exam, exam 4, you will take that during the exam week. We are close to the end. Okay. End the meeting.